Good afternoon. My explanation will be about the detectors of gravitational waves, and I will explain what a gravitational wave is, and well, obviously the detectors, and well, I explain. Uh, well, uh, I begin with an introduction of what the gravity, what is the gravity in general relativity. Well, in general relativity, the gravity is a curvature in space-time. But if there are changes on mass distributions or variations in accelerations or something like that, will create waves in space. Why? It's like a stone and a swan. What's happening? You throw the stone and the water oscillates and makes waves. It's something like that. If you change the the, um, the mass distribution of something, this gravitational change affects the space and time. And what's the particularity and utility? That they are not absorbed by dust, by intergalactic dust, because the wavelength of that waves it's higher than the electromagnetic wavelength. And well, here is a representation of two binary system where one mass, where two planets or something like that are rotating around the center of mass due to the acceleration there are these waves. Well, I will divide the work in experimental support, where it's a little bit of history, the characteristics of these waves, where the characteristics in frequencies, amplitudes, polarization, etc. I will do a comparison between the gravity waves and the electromagnetic waves, because both are forms to observe and to measure shows in the sky. It shows planets, it's to obtain information from different ways. Later I will explain the devices who aid us to measure that, to obtain gravitational waves or to detect gravitational waves. And well, there are, I will explain some types, but principally the Weber's bus, that is the oldest. The first types of these devices, and later I will explain laser interferometers that we can separate in Michelson interferometers and in Michelson interferometers of ground type and in the space type. Ground type is in Earth, is in land, in the space type is in space, obviously. Well, experimental support. Hughes and Taylor in '74 studied studied a pulsar that emits electromagnetic waves, radio waves, and he noted that the periodicity of the wave emission is not all periodic. The periodicity varies on time, but the periodicity is constant. And for that, he supposed that it's not only one pulsar, but two pulsars are rotating around his mass center. And well, he recorded the observed time of periastron. That periastron is the shortest point of an elliptical orbit to his center of mass. We have that. Then the periastron is the place where the distance is minimum. It's a planet, center of mass. This distance is periastron. He noted that there are systematic shifting in periastron. And what does mean that? What does mean this? Does mean that the orbits of the planets are shorter. The two planets, or the two pulsars are approaching to his center of mass. Why this occurs? Because the orbits lose energy. The pulsars lose energy. For what? For gravitation, radiation. See, the body are accelerated because he rotates, and for that he loses energy in form of gravitational waves. And well, this is the representation of the shift periastron time in years. And well, the characteristics of a gravitational wave. I will explain the frequency, the amplitude, and the polarization. The factor H is a factor who relates the elongation with the initial length of our device. It means H is equal to delta L divide L. And polarization, that there are two types, in plus and in X. The frequency can get values from 10 power minus 16 to 10 to 3 power 3. The wavelengths, well, like that, and each of these frequencies corresponds to different sources. For example, to 10 power minus 16, it's the primordial source because the wavelength is around, well, it is approximate the size of the universe. And for each of these sources and for each of these frequencies, there are an observational method. Well, but we are interested in these three. Why? Because these three we do it. See, we do the Weber bar, we do the land type interferometer, we make it. We make it. And well, this is the frequency maximum we can obtain of a gravitational wave.